All right, we are live. Hi, everyone. Thank you so much for joining us today for vLLM Office Hours number 21. It's hard to believe that we've had 21 sessions already, but also awesome to see all the people, all of you join us time after time again. So today we have a special guest. Jihua Cheng is here from University of Chicago. Jihua, do you quickly want to do a quick round of introduction and just mention what you'll be speaking on and then pass it over to Michael?
Yeah, great. Thanks, Sasa. Thanks for the introduction. So, hey, everyone. Nice to see you here. I'm Yihua. So right now I'm a fifth year PhD at University of Chicago, and I'm also a core developer at this LM Cache project as well as this vLLM production stack project. And today I'm going to share our very exciting experience at developing this during developing this vLLM production stack project, and I'm going to talk about the technical details inside the production stack. And yeah.
That's awesome. Welcome. Thank you so much. Michael, do you just want to do a quick round?
Yeah, welcome, Yihua. Yeah, my name is Michael. If you don't know me, I run office hours. I'm an engineer at Neural Magic and Red Hat, and I'm a committer on the vLLM project. So yeah, we'll cover a quick update.
Awesome. Thank you, guys. Can you go to the next slide, please?
Yep.
So just a couple of quick reminders per usual. So we love to make these interactive, so feel free to jump in anytime and start talking to us. If you have any questions, you can definitely just start speaking, or you can also use Zoom chat. We typically ask people to pull up Zoom chat right now and type in which country or city or state you're dialing in from. You can see the flags on the bottom of the screen right here of all the countries that have been represented. I'm sure there's many more that we haven't received the answers to, but please, can you just pull up the chat right now and tell us where you are dialing in from? So, Noel, welcome from Cork, Ireland. Last session, we actually added 3 new flags, which was a record in a while. So Rio de Janeiro, of course, Max, welcome. California, the Netherlands, Michael from Boston, of course, Austin, Texas, Israel. Thank you, David, again for your feedback on the recording. Boston, Massachusetts, Boston. Hey, Tyler. Decent amount of vLLM commuters on the call today, so make sure you ask all those tough questions. Toronto, Silly Willy, California. Yeah. Hi, Tadim. Welcome, Atlanta, Georgia, California, Boston. Okay, thank you guys so much for coming from all over the place. We're really excited to have you. So we are recording this session and it is also live streamed. So typically in the past, it took us 48 hours or sometimes even more to get the recording to you. So we're making a quick change right now, and the recording will be actually available immediately as we're streaming this to X, to LinkedIn and to YouTube. That recording will be right away after this call within minutes. So feel free to find it right there. And then I will also post it shortly after to our office hours page where you can find future sessions and all the other previous recordings. If you have any follow-up questions after this call, you can always find us in the vLLM developer Slack. If you haven't joined Slack, please do. There's always good discussions going there, and it's a great place to learn about all of the announcements as they happen. All right, so with that, I'm going to pass it over to you, Michael.
Thanks a lot, Sasha. Hey, everybody. So we're going to cover kind of what's new in the past 2 weeks quickly. The main focus here, since we haven't cut a release, we're very shortly going to cut a release, is I'm going to cover sort of the incoming vLLM v1 by default change. They should say automatic fallbacks to v0. So don't get too worried about your usage of vLLM breaking. But we do want to make you aware of how the default behavior of vLLM is going to change, and hopefully give you more performance seamlessly. Of course, today's topic is a deep dive into vLLM production stack by Yihua. That should be a really great presentation. Make sure to follow along in the slides and ask questions along the way. We'll have plenty of time to answer you at the end. Yeah, we have several office hour sessions coming up in the year. As a reminder, as always, if you're interested in giving a topic, give us a shout. We're open to guest topics coming from anywhere, how you're using vLLM and whatnot. And I think we're pretty booked up on the East Coast vLLM meetup, but you still can submit a registration for the waitlist.
We just closed registration, but since we love
Okay.
office hours and we love all of the attendees, if you just message me directly, either here or through Slack, I'm sure we can figure something out.
Yeah, I'm sure if you send Sasha an email, he'll do something for you. So yeah, thanks for that. So, as always, we kind of want to cover vLLM if you're not already familiar. It's the de facto standard in open source model serving. This is because it's fast and easy to use and permissively licensed open source inference server. It's just a pip install and vLLM serve away to serve you the model of choice. Um, and it has support for many, many, many dozens of model architectures. It constantly gets state-of-the-art inference acceleration research, and of course gets great performance on NVIDIA GPUs, but also has a diverse hardware backend support with AMD GPUs, Google TPUs, AWS Neuron, Intel Gaudi, and several CPUs seeing active development in the project. And what's not covered here in this star history update is we actually have broken 40,000 stars on the project. And as you can see, it's been pretty linear growth, which is really great to see. So thanks for being a consistent part of the community. And, of course, it has a wide variety. Of course, in terms of model support and hardware support, it has a large variety of inference features. So not just text models, but multimodal embeddings, reward modeling, fitting into RLHF workflows, many different types of quantization and advanced performant kernels for the latest NVIDIA hardware, and many different scheduling and inference optimization works like chunk prefill or dynamic split fuse, as well as many application level features like structured outputs, tool calling, log probs, many things that are useful for building real LLM applications. And then, of course, many different types of parallelism. We actually have some more to add here. So beyond tensor parallelism, pipeline parallelism, data parallelism, expert parallelism. So lots of tools for you to go and use vLLM as the core low-level piece of your distributed inference infrastructure, which Yeehaw is going to thankfully cover today. So that's on vLLM, on Neural Magic and Red Hat, what I and Sasha work on. We contribute a ton to vLLM. I'm a committer on the project, as I mentioned. We've worked on inference kernels, system overhead reduction. We've worked a lot on bringing vLLM v1 to you, so we're really excited for it to be enabled soon. We've worked on integrating Torch Compile, and of course, many production-level features like metrics, dashboards, open source integrations to make vLLM more production-ready for our enterprise users and you. So if you're interested in using vLLM in enterprise, of course, talk to us. We're happy to help you get there. We wanted to also call out a blog that we released last week on quantizing DeepSeek R1 distilled models and running these on several reasoning benchmarks, particularly long context ones as well, and just openly sharing and talking about if you do your quantization right with the standards that we've tried to bring to the open source community, you can see really good accuracy preservation and still see very good reasoning benchmark reasoning performance on models while still quantizing them pretty aggressively. So definitely check out that blog if you're interested in reasoning models. So now onto our main update on vLLM. So there's going to be a big release incoming. We're not going to call it 1.0. It's probably going to be 0.8, but we are going to enable vLLM v1 by default. This is critical for performance of the project, and from some of the graphs on the side, if you're deploying Llama, you're deploying standard text or multimodal models without using really exotic features, v1 should start working automatically on the latest release and just make your deployment more performant, both from a throughput perspective, but also from a latency SLA perspective. So improving your time per output token, improving your time to first token. Most importantly, without configuration. So removing the need for you to tune your chunked prefill, max batch num tokens, or max num requests, or other things like tuning the num scheduler steps for multi-step decoding. So to clarify, if you explicitly want to disable v1 and make sure it never gets activated in any case, you can set the vLLM use v1 environment variable that's existed for a while explicitly to 0, and you will always, run on v0. Some things I wanted to go, kind of share about, and to be clear, vLLM v1 will fall back to v0 if there's a feature that you're starting the server up that isn't supported, like a model. Like if you're running an embedding model, we're going to use v0 right now. It's not supported yet in v1. If you're using FP8 KV cache, we're going to run on v0 for right now. If you're using, Xformers or FlashInfer as your attention backends, we're going to use v0 for right now. But this should happen automatically by default. But still, it's important for you to know what should you expect to run in v1 and see the performance benefits. And really, it's kind of all the types of parallelism. Particularly, we're adding data parallelism in v1. Text and multimodal models, basically across the board, are supported. There's only a few multimodal models that are still getting over the hump. CUDA, ROCm, and TPU all have v1 backends now, but for the other hardware backends, those are going to be on v0. Hopefully migrating over time. We brought our most performant attention backend, so Flash Attention, that includes v2 and Flash Attention 3. All the MLA backends, so Flash MLA, Triton MLA, these are going to run. So, we've certainly made it a priority for DeepSeek v3 to be enabled and really fast on vLLM v1. Prefix caching is supported. It's actually enabled by default in v1, so there's no need to specify it. And through how we've made v1, there's very little to no performance overhead, so we can enable it by default. We've also supported structured outputs, however, just with Xgrammar as the current structured outputs backend. So if you rely on some features in like outlines, for instance, that's not supported yet, and you should explicitly use v0. But we are working on bringing outlines and other structured output backends to v1 to expand the full support there. And speculative decoding is mostly not supported in v1 yet, but ngram is currently supported and really fast. We're working on making this optimized, and we hope ngram can actually be on by default and give no performance degradation, only give a performance win. Log probs are supported, so your eval should work. You will need to disable prefix caching, but we are very quickly working on making this work with prefix caching, which has been a requested feature for a long time. And LoRa should be supported, although we're still working on optimizing it further. It should already be faster than performance in v0, which is great. There's some features we plan on not bringing to v1, or are certainly kind of left to community or research to add into v1. We haven't found specifying different preemption modes to be useful. So we just do sort of the standard recomputation preemption by default. Multi-step scheduling has been removed entirely from v1. It's a single-step process, and multi-step just isn't needed anymore for performance, and it removes a lot of complexity to get rid of it. So we're happy to leave that in v0. We've supported most sampling methods, but we have deprecated best of just because we don't see a lot of usage, and it's been deprecated by most APIs, and just adds unnecessary complexity. However, parallel sampling, as in with n greater than 1 and beam search, are supported and will be supported. Other things we're removing are per request logic processors. You can still specify custom logic processors, but you should only be able to do this through the offline LLM API, or basically when you're starting the server up, you need to specify your custom logic processors. We're not allowing it on a per request basis. And also, we're not planning on adding prompt adapters, so kind of keeping the the adapters just to the LoRa style. So that's all I have to cover this right now. Please ask questions in the chat or in the QA. If you have any questions about this, we're happy to talk and guide you through what features you need or aren't supported, any concerns. Of course, we want to make this a seamless upgrade for you. So without further ado, I'd like to hand it off to Yihua.
Great, great. Thanks, Michael. Thanks. Let me quickly share my screen. Okay. So I guess everyone should see the screen right now. Right.
Yeah, it
Yeah.
looks good.
Okay, great. So again, thanks for joining, and I'm very excited to present our vLLM production stack. So yeah, today I'm going to cover the how does our like vLLM production stack covers solve this efficient multi-node vLLM deployments problem. And here's an outline of my today's presentation. So first of all, I'm going to give a brief introduction to the vLLM production stack project. And then I'm going to talk about the two main technical stuff in the production stack. One is optimizations in the request router, and one is optimizations in the heavy cache delivery. And finally, I'm going to cover some roadmap of the vLLM production stack. Okay, so let's get started. So first of all, what is production stack? So currently, the production stack is a community-driven project under the vLLM project that focuses on the large-scale deployment of vLLMs. So basically, first of all, it's community-driven, means that the multiple parties in the community are actively contributing to the production stack project, including IBM research, including Red Hat, including vLLM team, and including many different people from many parties. And the goal of the production stack is we're trying to focusing on the production deployment, basically by providing some interesting features around the vLLM, including fault tolerance, request routing, auto scaling, lower management, observability, all of those kind of things. And also, we are going to make it the production stack cloud native, means that it should support the Kubernetes ecosystem as well as the popular cloud providers. Yeah, and here is the QR code is our GitHub page. Feel free to scan it and yeah. So yeah, before talking about the technical details, this is a brief motivation about why we are going to have this production stack. So basically, vLLM right now is actually I would say it's the best serving engine right now. So it can serve the large language model request on the single instance with a very high performance and very good scalability. However, serving the vLLMs at scale is still pretty challenging. So there are multiple common pain points we heard from the community, like how to do the cloud native deployment of vLLM, how to reduce the latency, reduce the cost when really serving the production workloads, and how to do this load balancing and request routing smartly to like best utilize, let's say, prefix caching, right? And also, there are some pain points about the fault recovery and auto scaling stuff. Yeah, and the production stack is going to we are going to focus on solving those problems and let people to deploy the vLLM in a distributed environment. And here is I'm going to show the overall architecture of the production stack. So first of all, we have the core of the production stack consisting of like the vLLM and request router, the LoRa management part, the KV cache network for better KV cache offloading and delivery across different vLLM instances, and also the like metrics, the observability and metrics collection. And we are running this core on the we are also having this integration layer to integrate this core to different kind of cloud native platforms or different kind of hardware infrastructures. Like for example, Kubernetes integration, we are going to have the right now we already have the Helm chart. We already have those Kubernetes deployment YAMLs, and we are right now working on the CRD to make the production stack more like cloud native, more like an operator. And also we're going to have some Ray integration to integrate the core logic on the Ray cluster. And below that is the infrastructure. Basically, it's state-of-the-art stuff if you're running Kubernetes on distributed servers or you are deploying Ray on the distributed servers. You can try to use the production stack with those with our integrations. And here I'm going to list some core features and components in the production stack. So first of all, we want to make the production stack user-friendly, which means we already support this so-called one-click cloud-native deployment. And also we're having some observability dashboards built into the production stack. Everyone can. So we have a reference implementation of how the observability stuff should work. And the next thing is about the performance. So the production stack can help improve the performance of the distributed vLLM serving by two things. One is smart request routing, basically providing better load balancing features, as well as utilize more about the vLLM's prefix caching mechanism. And we also have this KV cache delivery network, which enables vLLMs to share KV cache across different instances. And I'm going to talk about more details about this KV cache delivery network later. And also, we are going. We already supported and are also going to support some those production-ready features, including LoRa management and also advanced auto scaling and fault tolerance features. So to deploy the production stack, it should be pretty easy. So we have this Helm charts for everyone to easily deploy the production stack just through one command line, one command. And we also have a lot of like useful tutorials covering like how to install a basic Kubernetes environment, how to install the production stack on the using the Kubernetes, as well as how to install the production stack on, let's say, GKS, EKS, and GKE, those kind of environments. So we're working on the official documentation site, but feel free to scan this QR code, and we have a bunch of well-written tutorials in our GitHub repo. So as a high-level introduction, so I also want to highlight the performance of the production stack. So basically, with routing algorithm and the KV cache sharing techniques enabled in the production stack, it can achieve the lower delay and higher throughput than the state-of-the-art other open source solutions. So here, these figures, to produce these figures, we are trying to run a real production workload of multi-turn conversation chat. There are like 80 concurrent users chatting with the large language models, and we are trying to set up inference, set up the production stack as well as a baseline on two servers with A180 gigabytes with the Llama AB model. And as you can see here, the x-axis is queries per second, and the y-axis on the left hand is the time to first token, basically the response delay, and the right-hand side is the time per output token, basically the generation speed. And on both metrics, the production stack can be better than the state-of-the-art, like the open source solutions. Yeah. And we also, those benchmarks, the scripts, the workloads, the tutorials are also available, publicly available with pretty detailed instructions on our GitHub pages. So just feel free to check it out if you're interested. And more results, we recently released the latest blog with, so just feel free to scan this QR code if you were interested in. So in the blog, we have a more comprehensive performance benchmark with multiple different setups, including different models, different workloads, different QPSs, those kind of things. Oh, I just saw a quick question from the Zoom chat. Are we going to support disagree preview and decode instances with core, and will it support independent scaling of P&D instances with proxy server embedded in router? Yeah, that is a good question. So we do plan to do the support So we're right now working on designing the interfaces of this prefill and decode discrete prefilling. And we're so those features will be released soon. And another quick question is it using the Kubernetes Gateway API inference extension? Yeah, this is a really good question, and I'm very happy someone asked these questions. So basically, right now our router is the core logic in our router is already in the production stack in the production stack GitHub repo, and we do plan to have the integrations with both like Kubernetes Gateway API as well as Envoy to make it more, better match those kind of production standard. Yeah, and that's already on our roadmap. Okay, let me try to move on. So now I'm going to talk more details about the router in the production stack. So first, basically, what should the router do? So vLLM, as we all know, is trying to serve each individual request at the best speed. But on the top of vLLM, there is a lot of different kind of needs. For example, where to send the request, how to balance the loads, and what if a VM dies, and maybe we also want to add some customized logics into request routing. Oh, by the way, I saw a lot of questions coming up, but let me try to first go through the slides, and when I goes to something like a checkpoint, I can answer the.
That's a great idea. You heard.
Yeah. Cool. So let me move on. So basically, the router is we see a lot of needs from the community, and we are trying what we are trying to do here, achieve here by the router is we want to achieve those community-driven features, and also we're trying to make the router easy to customize. So for the community to add the customized features. And right now, the feature here, I'm going to talk about give a quick overview at the router's features. So first is router supports smart routing and load balancing. So basically, what we support is we support session stickiness. We support the prefix aware load balancing. I will go through the details later. And we also have a extendable interface for new routing algorithms. And then we have this so-called fault tolerance by request migration. I will also cover the details later. And we are also adding those so-called NLP aware routing features into the router. Basically, it can support like semantic caching. It can support like personal identifiable information, like so-called PII detection. And those features are all contributed by the community, I think, from Red Hat. And also right now we're a Python native, which means that some core logics, those intelligent decision-making logics are written in Python, but we're having some benchmarks to make sure that the performance is, there is no big performance overhead introduced in the router. And basically the router's role in the system is trying to send the user request to the different vLLM deployments running different models, and it will also select a single instance or a single pod within the vLLM's deployment based on maybe the prefix aware stuff or the load. And also the route in our roadmap, we think the router should also be able to route the request to some external providers. For example, if it's going to route the request to ChatGPT or like cloud, those kind of different external providers, the router should also be able to achieve this. And also we want to add those, the semantic caching or request caching mechanisms, so to support different kind of optimizations. Yeah. And here is a technical, a little bit more technical stuff. It's the core modules of the router. So basically, when the user is sending the request, so the router is split into two parts. One is the request forwarding module, which does this request forwarding, HTTP processing, those kind of data plan stuff. And then there is a core routing logics, which is which we will keep it in Python for maybe for a long time, but for extensibility. And when the user's request is coming in, it will go through multiple extendable modules, including the request rewriter, model routing logic, instance routing logic, and finally go to the vLLM instance. And in the routing logics part, the model routing logic will first select a model, for example, select between Llama 8B or Llama 70B from this like pre-configured backend list. And then there is an instance routing logic. Basically, after we select the model, and we want to select the exact replica, which replica it should goes to based on the loads or based on its the statistics of each instance. And there is another service. There is another service discovery module helps the to detect the failures or the auto scale of different replicas, so that the router can keep up with the latest updates in the cluster. And let me introduce more about the instance routing logic. So basically, what we're going to do is here we want to select the best vLLM instance to execute the request. So in the production stacks router, we have two different components to collaborate to work together to select the vLLM instance. One is called the overload detector, which is basically working on the load balancing stuff, and it detects which instance should not be used. And there's another module called instance affinity module, which determines which instance should be used. So for the overload detector will first, based on the statistics monitored from each vLLM instances, it will generate a message about generate a data structure called available instances, and it will be put into the instance affinity module to generate the final instance. And in the overload detector, we right now have those like QPS aware overload detection. We have the KV cache usage aware overload detection. And for the instance affinity, we have session stickiness, we have prefix aware, we also have round robin, those basic solutions. And I want to quickly share the session stickiness and the prefix aware logic in the router. So for session stickiness, it is pretty useful in, like, let's say you have a chat application, right? Different users, they have different sessions, and each session they will have this own prefix, and it's better to route the same session to the same vLLM backend. So that's why we have this session stickiness. And on the application side, the router provides the same OpenAI API interface to the applications. And what you need to do is you just need to have some extra headers embedded in this OpenAI API. Let's say in this example, this extra headers is called my session ID, blah, blah, blah. And when using the production stack, you can just configure it to use session-based routing, session stickiness-based routing logic, and specify the session key to be the my session ID. And during the runtime, the routing logic will be like this. So if the session ID does not exist or has not seen before, has not appeared before, it will do the routing logic based on the QPS, and it will update the session ID inside the router. Else, otherwise, if the session ID already exists in the history, it will directly route the session based on the session ID. And also we have this prefix aware based routing, basically looking for the basically determine which instance will have the longest prefix matching. And this is right now a PR available PR in the contributed by Quintai, which is one of the core members in vLLM community. And the key technique here is a trunk-based tri-hash. So the input to the prefix-aware routing module is the body of the request, and first the routing module will trunk the request string and compute the hash value for each trunk, and then it will look up those hash values in the tri-tree and find the maximum match. And finally it will update the tri-tree with the hashes. So that's basically how the prefix-aware works. And also, I'm happy to talk about this request migration feature in the router. So basically, what we do is we will first, like when a new server engine dies or due to any other maybe multiple reasons, we want to migrate a request from one of the vLLM instances to another vLLM instance. The first thing we do is we will migrate the request KV cache from one vLLM to another vLLM. And then we will the router will reestablish the connection with a new instance without letting the user know. So I have a really quick demo here. This is already our so we are actively developing this feature, but we are happy, very excited to share this. So basically, when this demo shows that when one of the vLLM instance died, the default solution is basically the generation gets stalled. So as you can see here, after this is like in maybe 30 seconds, the request will just stall here and without generating anything. And after that, it will be just give a runtime error from Python. But if with the request migration logic, we can achieve that. Now, right now we killed the vLLM server died, but it can quickly migrate to a new server and continue the generation within like a few seconds. So let me maybe play it again. So here the previous connection is being migrated, and quickly the request will keep generating. Yeah, so that's about the request migration. And there are also some other functionalities in the router, including this request rewrite module, including the model selection module. We are going to have the semantic caching and semantic based routing. And also we have we use a Kubernetes API based instance discovery and fault monitoring inside the router to monitor the vLLM instances in the real time and update the router in the real time. So, and we want to say what we want to say here is basically since the core of the router is Python native design, so we hope that it can make it easy to extend the router with multiple different kind of logics, with multiple different fancy features, and it's much more easy for the community to contribute. Yeah, and for the future works in the router, first of all, we want to have this so-called CRD-based controller for the router to make it more compatible to the cloud or production systems. And we're also going to have this Envoy and Gateway API extension integration. And we are always trying to come up with better overload detection and those instance affinity algorithms for better, much smaller routing logics. And finally, we also have the plan to do this, to rewrite this, the data plan of the router using Rust or Go, those kind of more efficient programming languages. Yeah, and that's almost all about the router. Before I go to the KV cache part, let me quickly go through the question list. Let me see. So I saw the question from Mark asking any breakdown of the performance gain from different components such as router or Mcache, those kind of modules within the production stack. Yeah, this is really a good question, and I think we are going to release more blogs on the benchmarking stuff. So there will be some breakdowns.
Yeah, I think it would be interesting overall to see like like what different pieces cause different bottlenecks.
Yeah. That totally makes sense. And I would say both parts, both routing and KV cache migration are all important because I mean, if there is let's say if there is no KV cache delivery stuff, we are using vanilla vLLM, we still need this router to provide a better, functionality to improve the KV cache hit rate and reduce the cost and reduce the cost and latency. Yeah. And another question is about it's a production stack an alternative to the AI bricks, or can those be used together? So yeah, I think this is a good question. And right now we are on the same level to like basically providing a cluster-wide vLLM serving. And the key difference here is we are trying to keep the core more extendable, and we're going to we are all also we are more welcome to the the contributions from the community, and we're happy to see if anyone wants to contribute those new features into the router or into the KV cache stuff. We're more welcome. And also, since we're from the university, from the research lab, we are also happy to bring a lot of our fancy optimizations, not only including the router, not only in the router, but also in those KV cache stuff. And yeah, so that's about the production stack. And another question is the router a stateless component that can be scaled or actually as well? Yeah, that's a good question. I think so the short answer is yes. So the router is basically it will try to observe everything from outside, and it will not try to so the decision is made based on the the information from outside. So basically, if you want to horizontally scale the router, it's totally doable. And we are also trying to make the design so that multiple different routers will make the consistent routing decisions, so that when you scale the router, you don't need to worry about the different routers making different decisions on the same session or something. Yeah. And I saw another comments about the benchmarking vLLM stuff, which is great. We are definitely going to run those vLLM benchmarks on the production stack, and I think we are also going to contribute some to the vLLM for the for those distributed for workload that is more related to the distributed setup. And I saw another question about, is there a plan to support SGDown? Okay, this is a really interesting question. So right now the project is under the the vLLM project, but also since I mentioned before, we're treating the backends as basically OpenAI API endpoints. So it should be not too hard to integrate with SGDown. And also I heard from community that some people already runs it with Ollama. So I think the production stack will be flexible enough to support different kind of endpoints, and that's also what we wanted to achieve. Okay, great. So seems like I finished all the questions. Let me quickly move to the second part, actually third part, about this KV cache network in the production stack. So a little bit of the background about the KV cache. So the KV cache is a very good opportunity to boost the large language model's performance. So basically, if we can share the KV cache across the different serving engines, it can reduce the delay and the cost. And there are a lot of those kind of use cases that KV cache can be shared. For example, multi-turn conversation, or maybe RAG, or maybe long document Q&A, those kind of things, as well as the agent. Those scenarios, usually there will be a lot of like prompts being reused, and that's a best case for the KV cache being reused. And here in the production stack, we have this KV cache network module based on the mCache project, which is also an open source project on GitHub. And the mCache provides a good interface to do this KV cache sharing, and it also implements a bunch of the KV cache optimizations inside the mCache. And it gives us a few benefits. So the first benefit is the mCache. It actually provides a lot of optimizations to achieve a faster KV cache processing, including offloading KV cache from vLLM, injecting KV cache back to vLLM, and delivering KV cache across multiple instances. And the second benefit is that you can share KV cache across multiple instances. By doing this, it can not only achieve like better prefix caching across multiple instances, you can also do it, use it for like disaggregated prefilling. And the third benefit of the mCache is that we actually do have the upstream vLLM support. We have an official connector that is already merged recently into vLLM, and by running the vLLM, we can, without modifying any code, we can activate this the mCache module. So here I'm going to basically give a high-level idea of how it works. So during the request, after the request coming, after the prefilling is done, the KV cache is generated in the vLLM serving engine, and we can, by using the mCache interface, it can store the KV cache into the different storage devices, including the local storage devices like CPU memory or local SSD, as well as the remote storage server. Let's say if you have a Redis server, you can also store your KV cache there. And when the request come to another vLLM instance, we can retrieve those KV caches from the KV cache network and rebuild and inject the KV cache into the vLLM to skip the prefill stage. And in that case, we can reduce the response delay as well as reduce the GPU time. And yeah, so this slide is mainly about the upstream vLLM support. And you can see one of our key team members, Jiayi, has pushed the has created this PR in the vLLM and is being merged. And right now the official vLLM can support this disaggregated prefill as well as the CPU offloading with the mCache library. So let's talk more about the performance optimization stuff. So in mCache, we have done a bunch of performance optimizations about the KV cache offloading. So basically, the KV cache offloading, you can think about this as offloading the KV cache, dumping the KV cache from the vLLM page KV buffer to a continuous buffer which contains the KV cache outside the vLLM. And by default, a naive solution is we're just going to call CUDA mem copy async, or maybe just call like PyTorch tensors copy by using PyTorch APIs on every block and every layer. But this is a little bit slow because in vLLM, each page is just like 16 tokens, and the KV cache of that page is just a few KB. And if you call the memory copy on such a small object, it cannot fully utilize the PCIe bandwidth. It also has some, kernel launching overhead. Those kind of overheads makes it like much more slower. And our solution is basically we have those optimized CUDA kernels to copy all of the KV caches from all the blocks and all the layers at the same time within a single kernel launch. That makes it much more faster and makes it be able to use fully utilize the PCIe bandwidth when offloading to the CPU memory. And to support the KV cache delivery, we actually provide two different modes. One mode is called pooling mode. So basically, it's we are having a shared remote storage, for example, Redis, that can store those KV cache chunks, and the vLLM are calling the Mcache interface, and Mcache will do all those KV cache lookup stuff to say store and load the KV cache from the remote server. And in this case, multiple vLLM can share the KV cache from this shared storage. And there is another KV cache delivery mode recently being added. Is called peer-to-peer mode, which where we have a KV cache lookup server, which only stores the metadata of the KV cache and being very lightweight. And what the Mcache do is basically it will establish a peer-to-peer connection between different across different instances and transfer the KV cache without directly without passing it to the remote server. And another very important optimization is called KV cache prefetching. So basically, our insight is that the KV cache itself is very big. It can be several gigabytes or even tens of gigabytes. And loading the KV cache from remote takes a lot of time. And during the load, if we are not doing anything but just letting vLLM to wait, the GPU will be idle if the request is the GPU will be idle and the GPU utilization will be pretty low. And to solve this problem, we are using this KV cache prefetching. So basically, when the request come to the router will first trigger this prefetch call to notify the Mcache to first retrieve the KV cache to the vLLM. And after the KV cache is arrived at the vLLM, the router will then send the request to the vLLM. In this case, the delay of this request is not changed compared to the default solution above. But during the prefetch, since the vLLM hasn't seen this request yet, it will try to schedule other requests and keep the GPU busy. So this is a very useful optimization to improve the GPU utilization as well as without affecting the delay of affecting the latency of the request. And also another thing I want to mention is that the Mcache actually provides a pretty extendable interface for new storage devices. So basically, the Mcache will handle all the integration stuff with the vLLM, including the KV cache trunking, the token matching, the vLLM integration, the fast KV cache serialization, deserializations, and as well as other optimizations. And it also exposes a storage backend interface for people to integrate their own interface, own storage devices into the Mcache. So the interface is pretty straightforward. It has this put, it has a get, it has a prefetch, it has a contents. And if you want to do this KV cache offloading or KV cache storage, you don't need by using the Mcache interface, you don't need to care about the details about how vLLM will use this KV cache. You can just treat this as a purely extendable object store and put your code there. So right now there are already a few PRs in the merged or unmerged in the Mcache that support different kind of backends, including InfiniBand backend as well as different storage servers. Yeah. And finally, I'm going to, hopefully I still have a few minutes, so I'm going to quickly go through a few fancy optimizations in Mcache. First of all is, so those optimizations from the papers in our group. So the first optimization is about the KV cache compression. So what you can do here is, since the KV cache is large, it takes time to stream the KV cache around the different storage devices. What you can do here is you can compress the KV cache and make it much smaller, and then deliver it. The KV cache delivery as well as the KV cache offloading and injection will be much faster than without compressing it. And another use case is called the KV cache blending. Another optimization is called KV cache blending, which allows the KV cache to be concatenated together, and which is particularly useful in RAG applications. let's say in RAG, usually the application wants to concatenate multiple different documentations together in the input prompt, and if you have the KV cache for separate documents, you cannot directly reuse that, because let's say the document 2 here is not the prefix, and since it's not the prefix, it cannot be like automatically reused. But with our optimization called cache blend, we can quickly blending the KV cache of the document 1 and document 2 together to make it being able to use as if it's a prefix cache. So that's another optimization. And the third optimization is basically we call KV cache translation, where we can like translate the KV cache, share the KV cache between different kind of language models. So let's say in AI agent workflows, there is usually multiple different models, like or some base models using different LoRa adapters. And we have a paper called DruidSpeak, which does the KV cache translation to translate a KV cache from model A to the KV cache of model B. So we think that it will be pretty useful in the a lot of future use cases, including those agent workflows. And finally, we have this offline KV cache update optimizations, which will update the KV cache such that when we are reusing the KV cache again, the large language model will produce better answers. So we also have the paper out there. It's called steer. So basically, it will read the KV cache offline, trying to identify the important informations in the KV cache and try to augment the values for those important informations. And that's all about the KV cache optimization. Before the end, I'm going to slightly quickly mention the roadmap of the production stack. So we are going to first improve currently improve the documentation of the production stack, and we are also going to work on the cloud integrations, provide better cloud integrations to EKS or GKE, those kind of cloud platforms. And also we are having better Kubernetes support, including CRDs and controllers, as well as the integration with other community projects from the Kubernetes communities. And finally, since our core is mostly Python-based, so we're also very happy to extend the production stack functionality to Ray clusters, and we're going to have the Ray support. And like we always welcome the community to contribute, and just feel free to create any issues or peers or anything on our GitHub repo. And I think that's all. I'm attaching a few like QR codes about our community meetings, about the production stack Slack channel, and also our LinkedIn and X account. So feel free to scan this and follow us or join our community. Yeah. And that's basically all of my talk. Let me just quickly go through the question list, maybe.
Yeah, great job, Yihua. That was really great. I think like one question I want to call out from Vikram is where is the KV offloading buffer? Is it in CPU memory? I think
yeah, Michael. Yeah, thanks for the question. This is a really good question. So yeah, by default, the AM cache will offload the KV cache to CPU memory, but it can also have a hierarchical memory support. Basically, you have CPU, you have local disk, you have remote servers, those kind of places you can all those places you can store the KV cache.
Yeah. I think the clarification question is you can't do GPU transfer from GPU memory to storage directly, right? So GPU thread SM copy is not going to happen. So what you really need to do is like, okay, do it to the CPU memory buffer and then do from CPU memory buffer to somewhere else. So the question basically stems from like, okay, how is it handled? If you want to do a copy to a CPU memory buffer and then you want to do it to a storage, then are you keeping a double buffer copy here, or what do you do?
Oh, okay, good question. So right now we do have a like copy buffer. So basically the first thing is to the CPU. Let's use a disk as an example. So basically first what we do is we offload it to CPU, and then we will do this asynchronously with vLLM to write the CPU's KV cache to the disk. So we have extensively tested the performance, and such offloading will not impact the vLLM's performance. And another thing we want to mention is that since LM cache, as I said, LM cache is pretty easy to extend, we also have some like industry collaborations with the so-called the GPU direct storage. And we are happy to see from the by using those kind of advanced hardwares, we can directly offload the KV cache to the storage devices without copying it to CPU. Yeah, another question is about, does the KV cache support multiple producers and one or many consumers? I think, yeah, it does. So let's say if there is running the KV cache pooling mode, basically the KV cache is stored in a remote server, and you can have as many producers of that KV cache as you want. And for the peer-to-peer mode, I think it's a little bit more trickier. We are still testing the functionality, but I don't see any fundamental issues blocking the support of like one producer, multiple consumer. And the RAID support, the question about RAID support right now, so we're still working on that. And I think it's our roadmap, but we still need some time to finalize the design. But if you guys have any good ideas about how it should be integrated to RAID cluster or RAID serve, just feel free to create the RFC issue or submit a proposal on our GitHub. So we have a template for the proposal in the on our GitHub. So just feel free to check it out. And yeah, I think that's all about the questions from the Zoom chat. Any other questions or?
If there's follow-up questions, you can join the vLLM Slack. You should do that anyways, by the way. But there is the production Slack. You can see the QR code right there. Great place to ask questions. Yuhua, thank you so much. You crushed it. Really impressive.
Thank you,
Yeah,
Sasha.
very illuminating presentation. Yeah, I think we all appreciate it.
Thank you for hosting the office hour. This is great. And thanks to the community.
Yeah, we're lucky to have a very blessed community. Yeah, just to cover a few things just at the end here. Thanks for being a part of the community. Make sure to contribute and be an active part. Join the GitHub, join the Slack, join the discussion on RFCs, issues, PRs. We want to hear about your issues, your features you want implemented. You help develop the roadmap and what we focus on this project. And of course, build things on top of vLLM and tell us about it. If there's anything you'd like to see improved in office hours or in events and meetups, definitely let us know directly through emailing us or in the Slack openly. Yeah, we have the first East Coast meetup on Tuesday next week. And yeah, Neural Magic is hiring, as always, if you want to work on open source vLLM. It's a great gig. So that's all. Thanks, everyone. Have a great week.